Okay, friends, welcome back. Hope you've had a good couple of days. There have been some logistical questions that have emerged over the past couple of days. Some of you are wondering, what should I be doing? Should I be reading the text? Should I be doing the study guide? The study guide will tell you what portion of the text to do, to read, and what problems to do. Now, in this first sort of chapter, which I'm on the syllabus calling MO Theory, you're going to have to rely mostly on the study guide because Professor Smith, who wrote this text, doesn't use a lot of MO theory. I happen to think it's a useful frame of reference for thinking about organic reactions. You can do chemistry without worrying about it, but I find it useful. Because there's not a lot of it in the text, your first study guide is mostly stuff I have written for you. The introductory study guide, which reviews basic principles from general chemistry, does rely heavily on the text, and that's where you're going to find things like how to draw Lewis structures and how to assign formal charge and how to draw resonance structures. These are all things I think you should be good at already, having taken general chemistry. If you're not, you should definitely review that because you're going to see it on the practice exam and on the actual exam. In terms of what should you have done to prepare for today, well, ideally, since we're going to spend today and Friday and maybe a little bit of time on Monday on the MO Theory study guide, you should be about 2/3 of the way through that study guide. At the beginning, it's mostly just my writing, explaining stuff. Towards the end, there's going to be some learning activities and exercises that you need to do. Okay? By the way, a word about study guides and practice exams. Ideally, the way the course works best is if you're working ahead on the study guide, you need to look at the syllabus for what the planned schedule is. If we intend to spend, say, 3 days on the MO Theory study guide, then you want to do about 1/3 of the MO Theory study guide before each class. The process works best if you're not hearing stuff from me for the first time in class, but you've had some time to think about it ahead of time. Then after class, you should get started on the practice exam. I branded that assignment as a practice exam years ago because I know you take things seriously when the words practice exam are attached to them. However, it is more like an extended problem set of exam level difficulty. It is not intended to be a representation of the exact format and length of the exam. My exams are multiple choice. Don't let that lull you into a false sense of security, by the way. Just ask your TAs how easy they were. Some of them have taken my class before. But the practice exam is free response. The practice exam is also much longer than the actual exam will be. But it is intended to give you exam level practice so that you can know about the level of difficulty you should expect, okay? What that means is if you wait until, let's see, our exam is scheduled, I think, for closing February 2nd. If you show up on February 1st and decide, hey, I'm gonna take this practice exam, you should prepare yourself for, 10 to 12 hours of pain. I actually don't think it will take you that long, but if you wait until then to do it, you're gonna be overwhelmed. You should be working on it now, okay? So after we've done the MO Theory, after each class, you should go look at the practice exam and say, okay, what problems can I do now? And you should practice them, work on them, and that should get you going. All right. So, MO Theory, what are we doing here? Our goal is to get an idea of bonding in organic molecules that will help us, looking at the structure of an organic molecule, to predict how it's going to react. If you get that down in this early part of the class, much of what follows is going to be easier. If you're not able to do it, you're going to have to rely on memorization, and good luck to you then because there is too much to memorize to keep it all straight. So you've learned a little bit about atomic orbitals in general chemistry. These are the solutions to the Schrödinger equation that describe how an electron wave behaves in the presence of a positively charged nucleus. These are the familiar 1s, 2s, 2p, x, y, z orbitals. We're going to stick to the first and second row of the periodic table for the most part. And so these are the alphabet of orbitals that you'll be dealing with. But what about orbitals in molecules? How do we deal with the wave functions that electrons adopt in molecules, and how do we merge that with the idea of bonding? What you have seen probably in general chemistry and what is contained in the first chapter of your textbook focuses on what's called valence bond theory. And valence bond theory uses atomic orbitals to come up with new bonds, and bonds are considered as two electrons shared between two nuclei. So, for example, the valence bond theory picture of hydrogen would simply say, well, in hydrogen you have one bond. That single bond is two electrons shared between the hydrogen nuclei. That bond must come from overlap of the atomic orbitals on hydrogens A and B. And the only orbitals we have available, atomic orbitals to make that bond, are the 1s orbital on hydrogen A and the 1s orbital on hydrogen B. So that bond must come from overlap of those two orbitals together to make a new bond. If you want to draw how that would look in valence bond theory, here's a 1s orbital on hydrogen A, here's a 1s orbital on hydrogen B. You add them together in the bond between hydrogen A and hydrogen B, they would overlap to give you something like this. Okay? There would be, and that's sort of what you expect for valence bond theory. The only difference at this stage between the valence bond theory picture for hydrogen and the MO theory picture of hydrogen is that MO theory accounts for empty orbitals and valence bond theory doesn't. Okay? So this is what I was trying to get to last time. In MO theory, we generate the new orbitals for a molecule by combining the atomic orbitals for that molecule in all possible plus and minus combinations. There are rules for this process. We won't talk about them in class, but they're detailed in the study guide listed under MO theory rules that guide you sort of through this process. I don't totally think you'll need all of that to be successful in the class, but it's there for your reference. So, one combination, let's see, I gotta decide where I want this. Maybe it's better up there. All right. One combination of the 1s and A and B wave functions is for them to be added together such that their wave function signs reinforce each other. We talked about this last time. That's constructive interference, right? And you can see how, as we drew here, if we're plotting the 1s orbital from hydrogen A and the 1s orbital from hydrogen B, their wave functions add to each other in this interior portion. The purple is the sum of those two wave functions. That's our new bonding orbital, which comes from addition of 1sa and 1sb. That picture is exactly the same as we got from valence bond theory. And we talked about last time how you can think of this orbital as being lower in potential energy simply because one electron now gets to experience two nuclei. And you can think of it as being lower in kinetic energy because the slope of this wave function is changing less quickly over space. And remember last time we said that kinetic energy is related to how fast the slope of the wave function changes. That comes from a bunch of calculus and quantum mechanics. If you want to see some of those equations and see sort of how they're derived, you can look at the introductory study guide. There's a bunch of math there. It's designed mostly to scare you. You don't have to worry about it, okay? It's actually designed because I taught a grad level class on sort of OChem, and we really delved into that, and I thought it was cool. So I geeked out about it in the study guide. I feel bad about that because to some extent, you're just indulging my nerdiness. There may be a few of you out there who care about calculus, and if you do, you can go look at it and say, gee whiz, that's cool. For the rest of you, the conclusion that the slope of the wave function, if it changes less rapidly, if it's more spread out, the wave function is more stable, or alternatively, that electron delocalization spreading out is favorable and stabilizing, that's great. Okay. Now, the difference that I've said between MO theory and valence bond theory is in MO theory, we're going to account for empty orbitals and destructive interference between wave functions. So MO theory requires that if I'm going to make an orbital where I add two orbitals together to make a new molecular orbital, I have to make the opposite combination as well. I have to make the combination where I subtract one from the other. This is the destructive interference combination. We talked about last time how if you overlap the orange and the blue orbitals from 1s-A, 1s-B respectively, but they have opposite wave function sign, at some point in the middle they're going to cancel each other out and we're going to get a node. Okay, that's just, and remember, nodes are places where the wave function has a magnitude of 0. Okay, if we were to draw what this looked like, sort of drawn on to the structure of the hydrogen molecule, what we would see is there would be a node, which I'm going to represent with a dotted line here. It's really sort of a plane that is perpendicular to the page. And then we would have a lobe of electron, or a lobe of orbital in this direction and a lobe in this direction. I guess we'll continue to use orange and blue for opposite wave function signs, okay? Now, if you come from the perspective of potential energy, an electron, let's see, did I draw? No, I guess I didn't. We'll do the same up here for the plus combination. This would simply look like this with no change in wave function sign between the two nuclei. Now, from a potential energy perspective, if we put electrons in this minus combination orbital, do you notice that they're not going to spend time in between the two nuclei because there's a node right there? They're going to spend time over here and over here, farther away from the nucleus. So that should be higher in energy, right? Second, you'll notice that the slope is changing more rapidly. So from a kinetic energy perspective, because it's got to go through 0. So for both a potential energy and kinetic energy perspective, this orbital is higher in energy than our plus combination. So when we add two orbitals together, we get two new molecular orbitals out. One is lower in energy, and that's called a bonding orbital, and one is higher in energy, and that's called an antibonding orbital. And this is the real difference between valence bond theory and molecular orbital theory. Valence bond theory is going to focus on just the bonding orbitals. MO theory is going to allow for empty antibonding orbitals. And we're going to see next time, or maybe a little bit on Monday, how those empty orbitals are actually really useful in predicting what's going to happen to organic molecules. All right, questions so far? Yes?
Is it more likely to be a bonding orbital or an antibonding orbital?
Are you more likely to get a bonding orbital or an antibonding orbital? You have to get both, but generally only the bonding orbitals are filled. And we can actually follow up on that a little bit. The point I wanted to make is that the bonding orbital is lower in energy than these starting atomic orbitals, and that's why the bond happens, because it's more favorable. It allows the electrons to move lower in energy. The antibonding orbital is higher in energy than the starting atomic orbitals were. This is a minor point, but it might be useful for the discussion. This energy difference between your starting point and where the electrons are in the bonding orbital, this is you can think of this as something called bond dissociation energy, or how stable the bond is. We'll call this energy difference delta E with a B subscript to mean energy stabilization for the bonding orbital. We'll call this energy difference energy stabilization for the antibonding orbital. We won't worry about sign, but in general, what you will see is the magnitude of stabilization for the bonding orbital is always less than the magnitude of the destabilization for the antibonding orbital. In other words, the antibonding orbital goes up quite a bit higher in energy than the bonding orbital goes lower in energy. All right, I saw a hand, yeah. No, when I said that electrons get to experience both HA and HB, remember these are the nuclei, so two electrons in this bonding orbital are delocalized across this area between A and B, but they get to experience both. I'm seeing the source of the confusion. I'm using A and B for two purposes. Capital A and B are for hydrogens A and B. That's just what we're calling them. Lowercase a and b is antibonding and bonding. But, so the two electrons that are represented in this bonding orbital would be in this one, spending time between the two hydrogens. That's unfortunate. I should have called them 1 and 2 or something else. Did I answer your question, sort of? Yeah. In contrast, the antibonding orbital is empty. Now let's talk briefly about what would happen if I could add a couple extra electrons to hydrogen. Oh, I'm sorry. You had another question. Is constructive or the plus combination always bonding and the minus combination destructive interference always antibonding? Yeah, that's a general idea. Yep. Okay. Now, what would happen if I tossed 2 extra electrons in there? We're ignoring the fact that now you'd have H2, 2 minus, which probably isn't real, but what would happen? If I filled that antibonding orbital, let's just pretend. 2 electrons up top are now way more destabilized than the 2 electrons on the bottom. I've totally canceled out any benefit of being in this arrangement, and the bond's going to break. You don't know it, but we just derived, I guess for the first row, it's not the octet rule. Do you remember learning in Gen Chem that for the first row, you can only, whoa, I just threw the Apple Pencil, that's funny. You can only have 2 electrons in the bond between hydrogen, and you just memorize that because somebody told you, they must know, and therefore it should be 2 electrons. Okay, well, let's change things a bit. Let's say, let's change this picture and say, why doesn't helium bond to itself? Helium also comes with a 1s orbital. Excuse me. So, so the picture for helium, if we try to make helium-2, would be exactly identical to these 2 molecular orbitals we just made. We'd have a bonding orbital and an antibonding orbital. What would be the difference between helium-2 versus H2? How many electrons? Yeah, does helium have? 2 more electrons. Helium comes with 2. Each helium has 2, so you got 4. So for helium-2, we would have to populate both the bonding orbital and the antibonding orbital. No benefit at all. Okay? Not a magic rule of 2. It's just the fact that, I mean, you can think of it that way. It's just the fact that if you have that many electrons, you populate antibonding orbitals, you cancel out the bond. It's not favorable to form. Yeah?
So when determining if 2 atoms are going to bond together, you kind of put the bonding orbitals up against the antibonding orbitals. If there's more bonding, they'll bond. If there's more antibonding bonding, they'll just kind of fall.
Yeah, in general, you can use that. If you want to see if a molecule is stable, the bonding orbital should be filled and the antibonding orbital should be empty. Yeah, yes? Yeah, is that why the noble gases in general don't form bonds? And yeah, it's because you would have to fill antibonding orbitals. Yep. Okay, yes?
So in general chemistry, we would have learned that you have 2 electrons in the bonding orbital, or in the 1s shell. If you add another one, it would go theoretically to the 2s shell. And
Okay.
so is that comparable to?
I think what you're saying says, well, you learned 2 electrons first go in the 1s shell, and then if you have more, it goes in the 2s shell. That's for a single atom, and that's right. We're talking about now how you take 2 atoms, or more than 2 atoms, put them together to form a molecule, and then how do you account for the electrons in that molecule based on the orbitals that form. We're starting with a very simple molecule, in this case, just 2 atoms. Yeah. Other hands, yes?
What happens if the antibonding orbital is partially filled? What if there's only 1 electron?
Ah, that's interesting. What happens if an antibonding orbital is partially filled? What if there's only 1 electron? I don't know. You look at the energy and tell me, what do you predict? It's not as stable as if the orbital were empty, but it's probably not as bad as if it were full. So, and in fact, what you just did was predicted the existence of He2+, That's a helium dimer with 3 electrons instead of 2. That is actually, I think, known in the interstellar space or perhaps on the surface of the sun. I don't know. So yeah, it's not as stable as a full bond. It'd be worth about half, perhaps less than half of a bond. See in other hands, yeah.
Yeah, it's like the offset in the stability of the bond, that little the delta ether. And is that always symmetrical for the anti-bonding orbital?
Is it always symmetrical, the offset between, your sort of break-even point where the atomic orbitals were? No, the antibonding is always more destabilized. This one's always bigger than this one. That's called closed shell repulsion, for those that care, which is nobody but me. But it basically is the reason why you don't form why noble gases like helium don't bond. Yeah, because if they did, it would be worse than if they were farther apart. All right, there were some over here. Did I answer your questions? Nobody? No takers? Yes? Okay, yeah.
One more time, what is the orange and blue?
Orange and blue simply represents the sign of the wave function. So notice, yes, I'm using it for multiple purposes, which is also bad. Sorry. Here in this drawing of the antibonding orbital, what we would mean is the wave function here is positive and here it's negative, or vice versa. Important is that it goes through 0 in between the 2 nuclei. Yeah? Can individual electrons spend time in both filled and empty orbitals? No. Both orbitals exist. What do you do with an empty orbital? You think of it first as the place that, if you had another electron, the place it would go. You think of it also as the place where if you had energy, if you shot light at this molecule and had a photon that could cover this energy difference, then you could promote an electron to an antibonding orbital, and that would also break the bond, by the way. Okay. Incidentally, the fact that you can see at all is because photons of light are striking a molecule inside your retina, and you're exciting an electron from a bonding orbital to an antibonding orbital, and that's causing some changes. We'll talk about that more perhaps a little bit later in the course. But this kind of thing, excitation of an electron from a filled orbital to an empty orbital, is going on all the time around you, and it is in fact why you can see. It's been occurring like gazillions of times in the amount of time it's taken for us to describe it, which is really kind of cool. Okay, so filled orbitals, empty orbitals, important principle, the existence of antibonding orbitals, and that if you fill that antibonding orbital, you're going to break a bond. Let's make the molecule just a little bit more complicated, and let's look at, say, methane. I'm going to draw the Lewis structure of methane. I hope you can review the text so that you know how to draw on paper representations of three-dimensional molecules. The wedge means that hydrogen is coming out at you. The dash means the hydrogen is going back into the page. That's a representation of a tetrahedral carbon. The lines that are straight are sort of interpreted to be in the plane of the page. So you need to develop skills to be able to visualize molecules in 3D while drawing them in 2D. If you don't have a model set that can help you with this, that might be useful to you, and the syllabus talks a little bit about that. You might want to get that, and at least you can use them on exams for sure, but you want to build up enough intuition and familiarity with molecular structure so that when you get to the exam, you basically understand as you're drawing on paper what the shape of the molecule is. Okay, so this is tetrahedral, 109.5-ish degree angles all around. At this point, valence bond theory had a problem, and that is if you go back to our initial atomic orbitals that we had, the valence orbitals 2s, 2p, x, y, and z, they're not pointing in the right direction. And valence bond theory says bonds come from direct overlap of atomic orbitals. And so these are the z orbital, the p orbitals are all 90 degrees with respect to each other, and the 2s orbital isn't pointing anywhere, it's just a sphere. So to deal with this issue, Linus Pauling invented the concept of orbital hybridization, which was doing matrix math, really. So at that point, we're all asleep because we no longer want to hear anymore. Doing math to add these 4 orbitals together, 2s, 2pz, 2py, and 2px, then dividing by 4 to make 4 identical atomic orbitals that Linus Pauling called hybrid orbitals. So you've heard of orbital hybridization, right? You know what an sp3 orbital is? That is an atomic orbital that is 25% s and 75% p. The superscript just represents, we could put a 1 on the s, but we don't bother because why? Because you can tell there's just 1 there. 1 part s, 3 parts p. That just means we've mixed all of these together, all of the 2s, 2p, x, y, and z orbitals together, divided by 4 to get 4 new sp3 atomic orbitals. Okay, so, and it just so happened that those 4 sp3 orbitals are oriented, the math works out beautifully, 109.5 degrees away from each other, all lined up with those bonds between carbon and hydrogen. So you can envision a bond between carbon and hydrogen in methane as coming from a 1s orbital on hydrogen, there we go, and then an sp3 orbital on carbon that's pointing towards the 1s orbital on hydrogen. I've drawn for you the shape of an sp3 orbital on hydrogen, on carbon. As I said, it's 75% p, so you'll notice like a p orbital, it has a node at the carbon. You know, a regular p orbital looks like this with a node at the nucleus. So does an sp3 orbital. But because of the s spherical character, one of the sides of the sp3 orbital is distorted relative to the other. So you have this sort of balloon-shaped orbital where one of the lobes is bigger than the other, and there's a change in wave function sign at the nucleus. But the basic idea is from valence bond theory that you get end-on-end overlap, of the 1s orbital on hydrogen and the sp3 orbital on carbon. End-on-end overlap, we're going to call sigma type overlap. And because of that, we'll use sigma in a way because the overlap is what we're going to call cylindrically symmetric. That is, if you take the little hydrogen on the end and you twist it around, it doesn't change how the orbitals overlap with each other. We'll call bonds that come from end-on-end overlap of atomic orbitals sigma bonds. You may have heard that term before, it might be new to you. Another way to describe a sigma bond is to say it's a single bond, okay? Right, does that sound familiar? You probably thought of that a little bit before. Okay, yes?
You said that it's 75% P.
Yeah.
And 25% blue. So is the little blue part there representative of the S characteristic and the orange is blue?
No, the blue part, if we were to look at, let's see, a p orbital, just 100% p orbital, it would be, there would be a change in wave function sign on one side versus the other. A 2s orbital, if we go back up here, is a sphere, though it also has a change in wave function sign inside versus outside. When you make the sp3 orbital, it basically looks like a p orbital, only one side's bigger than the other. Yeah, so the blue and the orange represent the mathematical sign of the wave function. If you could say what the number was here, is it positive or negative? And there's a switch as you go from one side of carbon to the other. Yeah.
Maybe I missed it, but could you explain why one side is bigger than the other?
Why is one side bigger than the other? I mean, the real answer to that, you would have to actually do the math to add the orbitals together, the 3p orbitals, and then the 2s orbital. I guess the best way I can tell you to think about it is to start, because the orbital is 75% p and 25% s. What you do is you just start with the p orbital and then say, how do I make that look a little bit more like a sphere? And you just inflate one side instead of the other. The answer is it falls out of the math, and I realize that's unsatisfying. Okay, what else? Yeah?
Does the sp3 orbital, is it going to be closer to the p or the s orbital?
Is the sp3 orbital going to be closer to p than s? Yes, because it's 75% p. So if this is the energy of a 2s orbital and these are the two p orbitals, you expect sp3 to be right about there. Okay, so on the other hand, yeah.
Are sigma bonds, are they always going to involve, like, will they ever involve the p orbitals?
Can sigma bonds involve p orbitals? Sure, you could have a p orbital overlap end on end with something else. Though for most molecules in this class, since we're dealing with carbon, sigma bonds are going to involve a lot of these hybrid type orbitals. Yeah. Yes?
So with the hybrid orbitals, like the sp3, it kind of looks like on the picture that like just the s orbital kind of exists on its own still up on the hydrogen. So does that still exist, and those are kind of like the hybridized orbitals, like middle of them? The overlap is, or is it like its own thing, or does it all exist at the same time?
No, so if I understand your question, the picture is showing a 1s orbital on hydrogen overlapping with an sp3 orbital, one of the sp3 orbitals on carbon. So if we were to draw what this new sort of, I've tried to show the overlap of those two. Let me just redraw the molecule. And then we'll say this sigma bond comes from overlap of the 1s orbital on hydrogen with the sp3 orbital on carbon. That combination actually is going to end up looking like this. In our drawing above, anytime the atomic orbitals overlap in phase with the same color or wave function sign, you get constructive interference, so they just add together and reinforce each other. So that's sort of what that new bonding sigma bond orbital would look like. Okay, yeah?
Do you ever have to distinguish and put a 2 in front of that sp3 because it's combined with 2s?
Right, do you ever put a 2 in front? You could, but people don't.
Okay, just because it's carbon.
Because you just, I mean, everybody assumes if it has p orbitals, it's got to be a second row element, so yeah. Okay, what we're going to add to this from MO theory is the concept of an antibonding orbital, okay? So in valence bond theory, we're going to call this, what I've just drawn, a sigma bonding orbital. And for the same reasons described above, electrons in this bonding orbital are going to be more spread out than they would on either of the atomic orbitals. So this bonding orbital is going to be lower in energy than the 1s orbital on hydrogen or the sp3 orbital on carbon. What we're going to add to that from MO theory is the concept of the empty antibonding orbital. Okay, so we've just shown you, let's see, if this is about the energy of the 1s orbital on hydrogen and perhaps the sp3 orbitals on carbon, that's sort of our break-even point. This axis represents energy. Over here, I'm going to draw the energy of the sigma bonding orbital. And I'll even draw it again, though I'm just, in this case, going to draw the carbon-hydrogen bond by itself. Again, there's a smaller lobe, a change of wave function sign at carbon, and then the large lobe envelops all the space between carbon and hydrogen. In MO theory, we're going to have to deal with an antibonding combination. We're going to call that a sigma star orbital, and this is going to come from the minus combination of 1s and sp3. Okay? So that would be if I brought together a 1s orbital. Let's see how to do this. If I brought together an sp3 orbital on carbon, oops. With an s orbital on hydrogen, but they now come together in the out of phase or opposite combination. And as I move them close together, they're going to start canceling each other out every place where the orange and the blue overlap because they have opposite wave function sign. So that minus combination leads to an antibonding orbital. As we saw above for hydrogen, there's going to be a node in between the two nuclei because, as I showed you above, as hydrogen approaches carbon, the wave functions cancel out everywhere there's overlap because they have opposite signs. We're going to get a node in between the two nuclei. There's going to be wave function here, not in between the two nuclei. There'll be a smaller lobe on this side pointing toward the node. It's smaller because it's been canceled out, and then a larger lobe pointing away from the space between the two nuclei. So if I'm following along with the sign of the wave function as we've drawn things, this is what that antibonding orbital would look like, okay? We get this by the minus combination of a 1s orbital with an sp3 orbital. A couple of things. People struggle with this because they wonder, as I thought about adding these two together, the big lobe was the blue one, but now it's small. Why does it end up that way? I have two answers that are perhaps equally unsatisfying. The first answer is the math makes it be that way. The second answer is, again, the blue lobe on carbon is smaller because after we've subtracted the two orbitals from each other, that blue lobe gets canceled out. And notice how I've drawn the orange lobe on hydrogen distorted so it's facing away from the node. It's mostly on the right-hand side. The reason for that is, again, as I brought the two together, there was canceling out such that all of this space, let's see, here we go. All of this space near the node is the wave function's gone to zero. Yeah?
So the orange lobe on the bottom carbon, is that supposed to be the same size as the larger?
It got larger accordingly. And an explanation as to why that is sort of beyond the scope. You're not going to have to do that. You will need to know that this is what a sigma star antibonding orbital looks like. An important consequence that we'll get to Friday or Monday is that this sigma star antibonding orbital, if you're sort of following along, the space between the two atoms is where the bond was. The antibonding orbital is on the hydrogen, but a lot of it is on the carbon and pointing exactly behind the bond, 180 degrees away from where the bond is. That's going to be important later on because we're going to need to know where that sigma star is to describe how some reactions proceed. Okay? We'll get to that in perhaps Friday or early Monday. So the MO theory picture of methane that we're going to use is going to account for bonding orbitals and antibonding orbitals. But again, we'll say that the electrons fill the bonding orbital and the antibonding orbital is empty. All right. Now we can do this for each of the 4 bonds in methane. And if we did that, we'd end up with a picture of bonding in methane that looked, we'll just do the orbital energy diagram for the whole molecule. We would predict 4 identical carbon-hydrogen sigma bonding orbitals and 4 identical carbon-hydrogen sigma star antibonding orbitals. Methane, looking at that structure, each line represents 2 electrons shared between those 2 atoms. So we have 2, 4, 6, 8 electrons. And so we will fill up the bonding orbitals until we run out of electrons. And so this is a picture of bonding in methane. We have 4 identical CH bonds, 4 empty antibonding orbitals, which are the place where more electrons would go. Okay. Now, your MO theory study guide says that MO theory can actually account for bonding in methane without using the concept of hybridization. And there's this little horrible figure in your study guide that shows you how this is done. You don't need to worry about this other than to look at it for a moment and let your brain explode. Because what I've shown you here and called it the MO theory picture is actually really just a hybrid of valence bond theory and MO theory. MO theory doesn't require you to think about electrons as being shared exclusively between 2 atoms. In fact, MO theory allows you to delocalize electrons over the whole molecule. So just for like 2 minutes, I'm going to show you the full MO theory picture for methane so you can get used to the idea of electrons not only being shared between 2 atoms, but being delocalized. The pure MO theory people, if you say, hey, I've got these 2 electrons and they're shared between those 2 atoms in a bond, the pure MO theory people are going to say, bond? What is a bond? What is this bond you're speaking of? Those electrons are not shared between those 2 atoms. They're actually shared over the whole molecule. That concept is useful in some contexts, and we will use it. But for our purposes, when I say MO theory, we're going to stick to this picture. 2 electrons shared in a bonding orbital between 2 atoms, and then empty antibonding orbitals. Just real briefly, I'll show you how you can take, so if we draw methane again, I'm not going to spend too much time on this, and this certainly will not be on your test. I can make a bonding orbital from methane by taking 4 1s orbitals on hydrogen and adding them to a 2s orbital on carbon. Adding together with the same wave function sign, I would generate an orbital, a bonding orbital, that actually envelops the whole molecule. And the 2 electrons in this bonding orbital don't belong to carbon or any of the hydrogens, they belong to all of them. Okay, so there's 2 electrons there, they're spread out conceptually over the whole molecule. I can write a combination where I take, and I'm only going to show you a couple of these. How do I deal with the p orbitals which aren't pointed in the right direction? Well, actually, they are pointed in the right direction for our purposes. I never know whether to go off on these tangents or not. Some students hate when I say things in class that are not going to be on the test. Other students love it because it takes up valuable class time that you're not responsible for. So I'm not sure which camp you're in. So if I were to draw what this orbital actually looks like, it looks like this. And I could draw 3 other orbitals using the alphabet that I've been given. But this gives you a sense that there is a way to approach bonding in organic molecules that loses the concept of 2 electrons shared between 2 atoms entirely. Because this class focuses on bonding and changes in bonds, we're going to stick with this picture for the most part. However, when it comes to resonance, and resonance delocalization, we are going to need to come back here and pick up this idea of fully delocalized orbitals. Before we do that, and I think we'll do that Friday, before we do that, I want to talk about bonding in a slightly more complicated molecule. Let's talk about ethylene, or if you insist on IUPAC correctness, ethene, which is a terrible name and nobody calls it that. This is the simplest alkene. Let's just talk briefly about shape, hybridization, and where the bonds come from. Carbon 1, carbon 2. Tell me, what is the geometry or the molecular shape around carbon 1? Trigonal planar. Very good. You know that because it's surrounded by 3 groups. Therefore, what is the hybridization of carbon 1? sp2. Good. Trigonal planar, sp2 hybridized. Bond angles 120 degrees. An sp2 orbital, there are 3 of them, and they are each 33% s and 67-ish % p, right? More s character. Left over, by the way, if we're going to do that, is an unhybridized p orbital. The 3 sp3 orbitals are all in the same plane, and the p orbital is perpendicular to those. Does that sound familiar? You got that? I'm not going to draw it. It's in the study. It's in the MO theory study guide. You better be good at that, by the way. If that's confusing to you at all, then please go read the study guide until it's not confusing to you. Let's account for each of the sigma bonds. The bond between carbon and hydrogen here comes from what? That's a sigma bond between carbon and hydrogen. What atomic orbitals overlap to make that bond? 1s on hydrogen and sp2 on carbon. What would that bonding orbital look like? It's actually going to look, yikes, just like that. We're going to draw all the hybrid orbitals. There are differences in shape a little bit in the shape of the largest lobe, but we're going to draw basically sp3, sp2, and sp hybridized orbitals is basically like this. Carbon-hydrogen bond is going to look like this. Okay. So the 2 carbon-hydrogen bonds are going to be that way. What about the single bond or the sigma bond between carbon and carbon? What does that come from? Overlap of sp2 plus sp2. We haven't drawn that before, so it's probably worth doing. You would do that by simply drawing an sp2 orbital and another sp2 orbital, and we would draw the bonding orbital by having the 2 come together with the same wave function sign. Anytime they overlap with the same wave function sign, that's constructive interference. If these are the 2 carbons, the bonding orbital is going to have a continuous lobe in between the 2 nuclei with smaller lobes in the space outside the 2 nuclei. This is what a carbon-carbon bonding orbital looks like. Okay? And it's lower in potential energy than the starting sp2 orbitals because the electrons in that orbital are more spread out and they get to experience 2 nuclei. While we're on the subject, because we're thinking about MO theory, we need to account for the carbon-carbon sigma star bonding orbital. That would come from opposite phase or opposite wave function sign overlap of the 2 orbitals. So you would bring them together such that orange would overlap with blue. Okay, everywhere they overlap, orange and blue, they cancel out to form a node. So we are going to actually pause there, and I'm going to leave it to you as an exercise to draw what that carbon-carbon antibonding orbital would look like. When we come back next time ahead, we're going to talk about what this other bond is and how it's made, and we'll move on from there. All right, thanks. Have a good Wednesday.